This is the YouTube video for investigation 4A, which is called Sensible and Latent Heating. And I think this is one of these videos that you're probably going to want to watch more than once. This investigation involves basically talking about the different energy exchanges that happen between water and the surrounding air, which is good because it's important, but it involves heat, in better words, energy exchanges of a couple of different names, which you probably are not familiar with. And there's more math than usual in this investigation. Now, the AMS and Bowling Green is really good about making sure that natural science gen ed courses don't really involve math beyond arithmetic. And in fact, this investigation doesn't involve any mathematics beyond arithmetic. But some of you are still going to get just a little bit anxious when you see the equations. And for those of you who are eCampus and may not have actually been doing any math for quite a while, this may really cause some anxiety. So I will be really good in this investigation, I hope really good, about going through some of the mathematics that you're going to be expected to use and how to actually do things. So let's get started. Let's get going on our PowerPoint. And again, Sensible and Latent Heating is the name of investigation 4A. Now what I want to do is I want to start with water, because water is actually really important in terms of what we do in meteorology. When you think about the weather, other than temperature, which is obviously an important component of our weather, most of our daily lives are basically governed by whether or not we're going to have to deal with water in the atmosphere, whether it's humidity or rain, sleet, freezing rain, or snow. But water is a big part of weather. And not only do we have to deal with water when we're talking about the weather, but we have to deal with the fact that water is constantly changing phase in the atmosphere. So it's going from water, and we have to be really careful here when we're talking about water. I'm going to be really careful, I hope, and stop using water to mean liquid. So water, basically, water, the molecule, is constantly cycling between ice and liquid water and vapor and then back again. So I'm going to actually try really hard in this investigation video when I talk about water to mean the molecule, and then just focus on solid, liquid, and vapor. So these arrows in this figure are basically meant to indicate all of the phase changes that water undergoes in the atmosphere, and there are 6 of them. I'm going to want to go through each of these individually just to make sure that we're all on the same page. First, there's melting. Now you'll notice that I've put a positive sign next to melting. Now the reason I've done this is because as water is changing phase, it is either gaining or losing energy to facilitate that phase change. And so as water is changing phase from solid or ice to liquid, it has to gain energy. So this plus sign indicates that water is gaining energy during the phase change. Now, you can't just fabricate an energy change. This energy has to actually come from somewhere. So as water is changing energy, it's changing phase from ice to liquid and gaining energy, that energy is actually being given to the water from the surrounding air. And so the water is gaining energy and the surrounding air is losing energy. I want you to keep that in mind, that this is an energy exchange. So the water is not just gaining energy, but the surrounding air is losing that energy and transferring it to the water. The water is absorbing that energy from the surrounding air as it melts. Now, if we continue on, evaporation involves an additional phase change, an additional gain of energy. So as water evaporates, as it changes phase from liquid to vapor, it is again absorbing energy from the surrounding air to facilitate the evaporation. So this plus indicates the increase in energy that the water experiences, but the air is losing energy. Now we go in reverse, and you can see we have our reverse arrows down here, and we see, first of all, for condensation, in this case, as water changes phase from vapor to liquid, water is actually losing energy as it's going down energy from vapor to liquid. And as the water loses energy, it's actually releasing this energy to the surrounding air. And then as water freezes and it changes phase from liquid to ice, the water again loses energy. It goes down phase in terms of energy from liquid to ice. It loses energy, and again the surrounding air is going to gain this energy that the water is losing. But these negative signs indicate that the water is losing energy. Okay, we have 2 more phase changes, And these are phase changes that you may not be familiar with. The first one is called sublimation. When water sublimates, it goes directly from the solid to the vapor phases. It skips liquid altogether. Sublimation occurs when the temperatures are cold, but a lot of energy is actually required for the water to go from solid directly to vapor. In fact, the amount of energy required is first the amount of energy required to melt this ice, and then second, plus the amount of energy that will be required to melt that liquid. So the energy required to sublimate ice is large, and it's occurring at a low temperature where there's not always actually a lot of energy around. So sublimation is a pretty slow process. Going in reverse, we have a phase change called deposition. Deposition occurs when water goes directly from the vapor phase to the solid phase. So again, this is occurring at a low temperature. Liquid is not involved at all. The vapor is changing directly to the solid. And when we have deposition, the water is losing a tremendous amount of energy to the surrounding air. In fact, the energy is lost is equal to the energy required to condense this vapor plus the energy then required to freeze the liquid. So again, deposition, a lot of energy required. In this case, the water is losing this energy to the surrounding air, but it's occurring at a very low temperature. So again, this is a pretty slow phase change. All right, now, as I move to the next slide, I'm going to show this particular image again. What I want you to keep in mind, and I was really careful to indicate the energy changes in terms of water gaining and losing energy. And the fact that the air is losing energy as the water gains, and the air is gaining energy as the water loses. But what happens to temperature during all of these phase changes? And this is what I want to talk about next. So I'm going to define our first heat term. And this is something called latent heat. Latent heat is actually the energy required to change the phase of water at a constant water temperature. And you'll notice that I've really kind of blocked off that constant water temperature. And the point that I want to make here, and it's an important point, is that as water changes phase, as water goes through all 6 of the phase changes that I described on the previous slide, the temperature of the water remains constant. In better words, all of the energy that the water is going to be gaining or losing during the phase change is actually going into the phase change itself. None of that energy is being used to change the temperature of the water. Instead, what's happening is that as the water is either absorbing or releasing energy to the surrounding air, the air temperature is going to change as a result of the air either losing or gaining energy. So let's talk about this. Just keep in mind that during latent heating, the temperature of the water remains constant during its phase change. So here is the previous slide. And now we have the complete figure from the investigations manual. And you'll see that I have latent heat absorbed from the environment on top, latent heat released to the environment on the bottom. So these arrows basically indicate whether the air is actually gaining energy or losing energy. So let's talk about this. And what you'll notice I've done here, I've just put in a dotted green line right through the middle of our figure. And you'll see why this is so in a moment. Now what I'm going to do is I'm going to start with melting, evaporation, and sublimation. And you'll notice that in each of these 3 phase changes, the water is absorbing energy or it's absorbing latent heat from the environment as it undergoes these 3 phase changes. Here are our plus signs, indicating that the water is gaining energy. Now as the water gains energy from the surrounding air during these 3 phase changes, the water temperature doesn't change because it's changing phase. It's undergoing latent heating. On the other hand, the air is losing energy. It's actually giving up this energy to the water that is being absorbed by the water. So the air is losing energy, and so the air is actually cooling. And so we refer to these 3 phase changes, melting, evaporation, and sublimation, as cooling processes. And I want you to understand, I just want to reiterate this. It's a cooling process. Each of these is a cooling process, not because the water is cooling, the water temperature stays constant, but because the air is cooling. So during evaporation, during melting, during sublimation, the surrounding air will cool. Conversely, during condensation, freezing, and deposition, the the water is releasing energy to the environment, to the surrounding air, as it undergoes these three phase changes. And so latent heat or energy is being released to the environment or the surrounding air as the water undergoes freezing, condensation, and deposition. So while the water temperature remains constant during each of these three phase changes, it is still releasing energy to the surrounding air. The air is gaining this energy, and so the air is going to warm up. And so we refer to these three phase changes, condensation, freezing, deposition, as warming processes, because the surrounding air will warm during each of these three phase changes. So again, this is a pretty big slide. There's a lot of information here. The important thing to keep in mind is that during these three phase changes, it's the air temperature that's cooling or warming, and the water temperature remains constant during each of the phase changes, even though it's either gaining energy, melting, evaporation, sublimation, or losing energy, condensation, freezing, deposition. So there's a lot there, and you might just want to stop the video here, go back a few minutes, and listen to this one or two more times until you're sure that you're confident with this content. So this takes us through latent heat. Okay, the next quantity that I want to define is sensible heat. So sensible heat is different than latent heat because when we get an energy transfer, but it does not involve a phase change, sensible heat will actually result in the substance that is gaining or losing energy actually also having a temperature change. So it's sensible. It makes sense. When an object absorbs energy, it gets warmer. And when it loses energy, it gets colder. So sensible heat is heat that actually involves a temperature change. So sensible heat is the total amount of energy a substance gains or loses during an energy exchange. And in fact, during that energy exchange, there will also be an accompanying temperature change. Specific heat is a little bit different. And this, again, you might want to just watch the slide once or twice before you move on to make sure that you understand the difference between sensible and specific heat. Specific heat is the energy required to change the temperature of 1 gram of any substance by 1 degree Celsius. So it's just like sensible heat, only we are now specifying that we're only going to be dealing with 1 gram of a substance. In our case, it's going to be water. And when we talk about that 1 gram of water, the energy required to change the temperature of that water by 1 degree Celsius, either warming the water as a result of absorption or cooling the water as a result of energy loss. But when we have specific and sensible heating going on, there's no phase change. So we're not talking about latent heat here. So this is when we do not have a phase change of our water in any of the three phases. Okay, so here are specific heats of ice, liquid, and water vapor. So here are our phases: solid, liquid, vapor. And you can see the specific heats. And so here's when we start to deal with our numbers a little bit. The specific heat of both ice and water vapor is 0.5 calories. In better words, the water is going to gain or lose 0.5 calories per gram per degree Celsius temperature change, regardless of whether the ice or the vapor is absorbing or releasing energy. Liquid water's specific heat is twice as large. So it's going to be 1.01 calorie per gram per degree Celsius. And basically what that means is it takes 1 calorie of energy for liquid water to either warm or cool by 1 degree Celsius for 1 gram of liquid water. Okay, so again, you might want to just watch this slide once or twice. It's not quite as complicated as the previous slide, but we're going to start using all this information as you work your way through the investigation. And this is where the math comes in. So I put our specific heat table up here at the top of the slide, and I'm going to start to show you the difference between specific and latent heat. So this is again from your investigation, and before I actually explain what this particular graph is showing you, let's make sure that we understand our X and our Y graphics, our X and Y axes. So the X-axis of this particular figure or table is energy in calories, from 0 on the left all the way up to 900 calories on the right. Our Y-axis on this figure is temperature in degrees Celsius. Remember that 0 degrees Celsius is equal to 32 degrees Fahrenheit. So this is freezing or melting right here at 32 degrees Fahrenheit. Everything lower is going to be a temperature below 32 degrees Fahrenheit, and we're going to assume we have ice. Everything higher, we're going to assume we have liquid. Ice has to melt at 32 degrees Fahrenheit or higher. And then if we go all the way up here, this is 100 degrees Celsius, and this is 212 degrees Fahrenheit. This is the boiling point of liquid water. And so basically anything above 100 degrees Celsius is going to be water vapor. All liquid water must vaporize once we get to 100 degrees Celsius, at least at sea level. And so what we have above 100 degrees Celsius is it's going to be water vapor. So for our purposes, we start with ice for temperatures below 0 degrees Celsius. We're going to have liquid between 0 degrees Celsius and 100 degrees Celsius. And we're going to have vapor when the temperature is higher than 100 degrees Celsius. So I think that's everything we need to begin to understand what the red on this diagram means. So what we're going to do is we're basically going to just start an experiment where we start with a temperature at minus 20 degrees Celsius, and we have ice. And we're going to begin to raise the temperature. So we're going to raise the temperature, and basically what's going to happen is the water is going to begin to absorb energy. And by water, I now mean ice. The ice is going to begin to absorb energy, where it takes 0.5 calories per gram of ice to raise the temperature of that ice by 1 degree Celsius. So the ice is going to absorb energy until it warms up to a temperature of 0 degrees Celsius. Now, once the ice is warmed to 0 degrees Celsius, it's going to begin to melt. But now the energy that the ice absorbs is going to be latent heat. There's going to be energy is going to be latent heat, and this is energy that the ice is going to absorb to change phase. So what you're going to see now is that as this red curve moves to the right, that means that the temperature of the ice is staying constant as it melts. Meanwhile, it is absorbing an increasing amount of energy. Now I'm going to click on this figure so we can see latent heat of fusion right over here, and you'll see it's 80 calories per gram. The latent heat of fusion is the amount of energy that 1 gram of ice must absorb to melt. And you'll see that the latent heat is much, much greater than the specific heat. So latent heat is a very large number. So in order to melt that ice at 0 degrees Celsius, 1 gram of ice has to absorb 80 calories in order to change phase from ice to liquid. And so we're going to melt all of this ice. And so as we're melting this ice, you're going to see that the amount of energy absorbed increases, and then our ice is going to be melted. Now, once all of the ice is melted, and we're just dealing with liquid water is going to continue to absorb energy. Now it's at the specific heat of liquid water, which is just 1 calorie per gram. So liquid water is going to absorb this energy. And as it's absorbing this energy, because there's no phase change, this is sensible heating. So the water absorbs energy and it responds with a temperature increase. And its temperature is going to continue to increase until it boils. Now, once this water boils, any of the energy that the water is going to absorb at this point is going to be used to change the phase of that water from liquid to vapor. So all of this energy is going to be used to evaporate the water as it boils. So you'll see the temperature remains constant at 100 degrees Celsius, 212 degrees Fahrenheit as this water boils and the liquid evaporates. And we're going to continue to be constant at 100 degrees Celsius until all of that liquid water has boiled off and all of that liquid has evaporated. Now, during the process of boiling that water, all of the energy that the water is going to absorb, that the liquid is going to absorb, is going to be latent heating. And the latent heat of vaporization is 597 calories per gram. So it's a huge number required to the specific heat for liquid water. So a tremendous amount of energy must be absorbed by that liquid water as it boils and vaporizes or evaporates. And I noticed as I was putting this PowerPoint presentation together that there's a spelling error in the investigation. There should be an R between the O and the I here. It should be latent heat of vaporization. vaporization, not vaporization. So just keep that in mind. Now, once all of that liquid water has evaporated as a result of boiling, and we're just dealing with water vapor, then what will happen is the vapor will continue to absorb energy, and now it will be specific heat. It will absorb energy, and every 0.5 calories of gain of energy for that water vapor will result in 1 degree Celsius of warming. So this basically takes us through the process of basically sensible heat, latent heat for melting, sensible heat, latent heat for boiling, and then sensible heat again. Now in the real world that we live in, what we're going to see is that latent heating for melting, for fusion, really does happen at about 32 degrees. But we know sensibly that liquid water evaporates. You don't have to boil it to get evaporation. Some of the molecules in liquid water at plain old room temperature will have enough energy to evaporate. So latent heating does go on at temperatures much, much less than 100 degrees Celsius. It goes on at room temperature. It's just that the water is not boiling and that only a little bit of that liquid water is going to evaporate when the temperatures are much lower. Now, here's where the math comes in the investigation. You're going to have to use 3 different equations to actually solve problems in our investigation. Now, I'm not going to solve the problems for you. I'm just going to explain how it is that you use the equations so that you can work your way towards the correct answers. All right, so the first equation that we're going to use in our investigation, I've actually just highlighted in pink here the variables in the equation, and these x's are just multiplication signs. All right, so for this first equation, m is going to be the mass of the water in grams. T is going to be the temperature in degrees Celsius. So this T higher minus T lower simply means the temperature change that the water is going to experience as a result of either absorbing or releasing energy. C is the specific heat of the water, regardless of phase, in calorie per gram degrees Celsius. Remember, for ice and for water vapor, this number is going to be 0.5. For liquid, it's going to be 1.0. And then this capital H is going to be the sensible heat, or the total amount of energy that the water gains, regardless of phase, in calories. And you're going to need to use this equation for questions 2 and 3. So for questions 2 and 3, you're going to be calculating the total amount of sensible heat that water either gains or loses given a specific mass, and then the specific heat depending on what phase of the water we are dealing with, and then the temperature change that the water experiences. Now, all we're going to be doing for the next equation is basically moving these variables around. So for questions 4 and 5, we're going to actually be calculating the temperature exchange that the water experiences given these other variable values. So again, capital H is going to be the sensible heating in calories, M is going to be the mass of the water you're dealing with, and then C is going to be the specific heat of the phase of the water that you're dealing with. So for questions 2 and 3, you're going to be given the mass, you're going to be given the temperature change that the water experiences, and you're going to be given the specific heat. So you'll know which phase of water you're dealing with. And then you're going to basically be calculating the total amount of energy that the water either gains or loses. For questions 4 and 5, you're going to be given the total amount of energy that the water gains or loses, as well as the mass of the water, and then obviously the specific heat, depending on which phase of the water you're dealing with. And then you are going to calculate the temperature exchange, or the temperature change that the water experiences. Finally, you're going to be asked to do a couple of latent heat calculations. In this case, mass is going to again be little m. L is going to be the latent heat, either the latent heat of evaporation or of melting. And then H is going to be the total amount of latent heat that the water absorbs or melts given its mass and this latent heat of melting or evaporation. So L is going to be the latent heat in calories per gram, and then H is going to be the total amount of latent heat in calories that the water is going to experience given the amount of water that you're dealing with. And this is going to be for questions 6 through 8. Now, obviously, as you're working your way through this, if you're having any difficulty at all while you're working through this and you're not quite sure how to do the math, Keep in mind you're not allowed to ask your classmates for the answers to these questions during the week that we're doing this particular investigation or lab. But you can still post to the discussion board or ask me in office hours how you set this up and how you actually use these numbers in these equations. So you don't have to work in a vacuum if you're having some issues. You can just ask me or your classmates how to better set these things up so you can work your way towards the correct answer. Now, given these values of specific heat and our phases, this actually does have an impact on our weather. So we're not just doing this to torture you. Keep in mind that the United States is a big place. And if you think about the West Coast, the Gulf of Mexico, and the East Coast, there are parts of the United States that are very, very close to water. And then if you think about the middle of the country, so you think about the Great Plains or the upper Midwest, you're talking about being right in the middle of the continent where you're a good 1,500 miles or so from a body of water. And this is a really, really big impact on the overall climate of the United States. So if you're really close to a big body of water like the Pacific, the Atlantic, or the Gulf of Mexico, then you're dealing with big bodies of water that are basically undergoing a lot of latent heat. And it's basically whether or not water is going to be evaporating or condensing near these big bodies. Okay, so what happens is a lot of energy actually goes into changing the phase of the water in the Atlantic, the Pacific, and the Gulf of Mexico, and not to really changing the temperature of the land masses that are adjacent to these bodies of water. On the other hand, if you're in the middle of the country, then you really are dealing much more with sensible heating than with latent heat. Now, one of the things that we don't really focus on in any great detail in this investigation is the sensible heat of land, of dirt, good old solid dirt or soil. And it turns out that the sensible heat of land is actually tiny compared to that of liquid water. So what that really means is that if you're on a landmass and you're right in the middle of the continent, and all you're dealing with is gaining energy from the sun as a result of absorption or emitting energy back out to space during the night as a result of it just being night and not getting energy from the sun, those energy exchanges need to really big temperature changes because the specific heat of land is so small. So what you see in a place like Minneapolis, which is our orange curve right here, is that during the wintertime, Minneapolis, which is really far away from all bodies of the water, Minneapolis is just basically dealing with sensible heat either gained from the sun or losing back to the atmosphere during the nighttime hours. And so Minneapolis turns out to be really cold during the winter and pretty warm during the summer. Now, if we consider Portland, Oregon, which is the blue curve right here, Portland and Minneapolis are basically at the same latitude. They're both at about 45 degrees north. And you'll see that I added this. This is not on the figure in the investigation. But Portland is pretty close to the Pacific Ocean. So if you're close to the Pacific like Portland is, what you see during the winter is that basically because a lot of the energy of the Pacific is going into latent heat and winds basically blow west to east, that Portland is pretty warm during the wintertime. So the energy is being used in latent heating rather than sensible heating, and so Portland has elevated temperatures during the wintertime. During the summer, you'll notice that Portland's temperatures are relatively close to Minneapolis's, but if you take a look at the annual cycle, you'll see that Portland's winter to summer temperatures are much smaller in cycle versus Minneapolis, where it's much colder in the winter and still hotter during the summer. So that's really the impact of much greater sensible heating in the middle of our continent, Minneapolis, versus latent heat adjacent to the coastlines and what we see in Portland. Okay, one last figure from our investigation, and I think this is I don't think this one fits real well, but I know you're going to have a couple of questions, so I just want to talk about lake effect really carefully. And of course, lake effect is something that really does impact our climate here in Ohio, particularly from points Cleveland and east. So basically what happens with lake effect is we get evaporation from Lake Erie, particularly during the wintertime when the lake is warm relative to the air that's flowing over it. And so when you have really cold air flowing over the lake, we get evaporation due to latent heat from the lake. And then this energy is then used to form clouds, and then snow falls over the landmass as a result of this air being forced up and over the mountains and the higher terrain just east and southeast of the lake. And so this is something that impacts areas from Cleveland east, particularly for those of you who are in Geauga County and Chardon in particular, which is probably the snowiest part of Ohio. Okay, so that's pretty much all I'm going to say about latent and sensible heat here in this investigation. I'm going to end this video now, and I'm going to post it on YouTube. But if you have any questions whatsoever, again, I know that these various terms are going to probably throw some of you all for a loop, and then layering math on top of all that is not going to help. So if you have any questions whatsoever, by all means, feel free to post them on the discussion board or ask me live during my office hours on YouTube. Again, fall session, that will be Wednesday evenings from 7:30 to 8:30 and Sunday afternoons from 2 to 3. But for now, that's it. That's all. I'm going to end the video, post it on YouTube, and I'll post an announcement to Canvas when it's ready for you to view.